Hello. In this video we're going to talk about acids or bases
happens when you add an acid or a base,
important thing we need to know how to
do,
do,
in particular,
because
to a
when
buffer.
we do titrations
And the
next,
reason this is important
a key step
is
in the
because
titration
when we
process.
get to the
So we're gonna
weak
start
acid
with this
strong
first,
base
'cause it's
titrations, which are going to come up next, we
Okay,
need to
so
know
you have a
what
buffer.
happens
Remember, a
when
buffer
you add
is a weak
acid or base
acid
to a
and
buffer,
its conjugate
because
base,
along the way
or
of doing
a
these
weak base and its
titrations,
conjugate acid.
you start with a weak acid,
Right?
then you
So when you
make
do
a
this,
buffer.
two things
as
are going to
you go.
happen.
One,
So
you're
you
going to
have
have
to
an
know what happens when you
acid-base
add acid or
neutralization
bases to the
reaction.
buffer.
And two, you're going to have new volume. All right, so the acid-base neutralization is the one we're going to focus on at the moment. And so when you add strong acid, for example, to a buffer, it's going to react with the base. So you're going to make more acid and you're going to have less base. Because you add strong acid, it takes some of the base that's already there and it protonates it to make it conjugate acid. Or in the other version of this, if you have the conjugate base of a weak acid as the base component in your buffer, then you're going to make less of that because you're going to protonate it and turn it back into the original weak acid. Conversely, when you add a strong base to the buffer, it reacts with the acid. So you're going to have the weak acid, hydroxide come together, it's going to make less weak acid, you're going to have more conjugate base. Or in the other version, you have the conjugate acid of a weak base, you put hydroxide in, it's going to turn it back into the original base and water, right? So you make more base when you add hydroxide to a buffer and you have less acid. Okay, that makes sense. This is probably best shown through example, so let me do that. So this is the example from the previous video where you have 1 mole of formic acid and half a mole of sodium formate added to water. And so here's the calculations we did in the previous video. Use the Henderson-Hasselbalch equation to find the pH of the solution. All right. Now here's the new bit that we're going to add some strong acid to this solution. So 50 milliliters of 2 molar HCl. What's the pH of this? Well, first let's find the number of moles of hydrochloric acid we added. So 2 moles per liter times 0.0500 liters, which is 50 milliliters, gives you 0.100 moles. All right, so we know how much hydrochloric acid we put in there. We still need to calculate the pH. Well, the pH is going to be driven by this in the Henderson-Hasselbalch equation. And so that means we need to find this ratio of base over acid, because the pKa of the formic acid is not going to change, and we're trying to solve for the pH. So we really need to just find the amounts of the base and the acid after we added this HCl. But remember, this HCl is going to change these concentrations because that's what acids do. All right, so looking at the two components, the hydrochloric acid, it's not going to react with the formic acid, part of our buffer, because an acid and an acid don't react together. But the hydrochloric acid will react with the conjugate base in our buffer, and it'll turn it back into formic acid. And it'll do this strongly, right? This is a forward reaction. It's not equilibrium. So however many moles of acid you add, it's going to do that much of a reaction and convert that much formate to formic acid, the conjugate base back to its acid. So remember, this step, there's no equilibrium. This is just stoichiometry. You know how to do this already. All right, so when we do stoichiometry, we need to do it in moles. When we do equilibrium equations, we do that in molarity, in concentration units. So often you have to convert back into moles to do this step of the problem. For this particular problem, we don't, because we're given moles in the problem. So that's fine. We can just use these. We don't need to do a conversion. And then we're going to do a reaction here. So we added 0.1 mole of HCl. It's going to react with the formate, and there's more formate than there is HCl, so HCl is going to be the limiting reagent here. And so what that's going to do is it's going to take some of this amount of formate and convert it back into formic acid. So this is going to be 0.4, because you're going to react away 0.1 of it. And this is going to be 1.1, because you're going to make more of it. Or, more precisely, here's the formic acid. Ta-da. So 1 mole plus the amount of hydrochloric acid that is turning formate into formic acid. It gives you 1.1. And then the formate, the base here, is half a mole, and then you subtract from it the amount of HCl that you added, and then you get 0.4. Okay, so now we have this, our amounts in moles. Now what are we going to do? So I'm going to copy this over here. Now what are we going to do? Well, hey, here's the Henderson-Hasselbalch equation. This is still a buffer. We did alter the relative concentrations, but we didn't change the fact that it's a buffer. So we can still use this equation. Now, this equation can be defined in molarity, which is how we started. So we could convert both of these, divide by total volume. Remember now, our total volume is bigger because we added 50 mils to the 1 liter, right? So our total volume increases. So we could divide both of these moles by total volume, but we don't really need to because the total volume would be in the denominator here, it would cancel out. So you can get away with using just moles in here, and it just saves you a step. So you can plug these moles straight in, and the pKa, and then you find the new pH after you've added the hydrochloric acid. So this is important for a couple reasons. One, this pH didn't change very much. Here it's 3.313. Before, it was 3.451. So if you had added this amount of acid just to plain water, your pH would have changed a lot. But we didn't do that. We added it to a buffer, so our pH barely changed. Which that's cool. That's why buffers are super awesome. Another thing that's important here is this is a step in a titration, and we do this a lot in this chapter. You have a weak acid, you're slowly adding strong base to it. What happens? So when you're in this region of the titration, you've taken the weak acid that you start with, and you've added strong base to it slowly, and then you've made a buffer. And so then these type of calculations are appropriate in that region before you reach the equivalence point. So we do this as part of titrations. So learn how to do this now, and it'll help you out through the rest of the chapter. So let me give you a procedural, right? So you have your buffer, and when you add acid or base to a buffer, 2 things are going to happen. One, you have the strong acid or strong base neutralize. And I'm assuming this is a strong acid or strong base, and thus it's a forward arrow. I mean, this is true if you added a weak acid to a weak base, but that gets complicated. So generally, we're adding a strong acid or base. And the strong acid or base is going to do what acids and bases do and neutralize the other one. All right, so it's going to do that. It's going to have its way with the solution. So you need to do stoichiometry, and you got to do that in moles. The total volume changes, but you can ignore that if you use Henderson-Hasselbalch in moles to find the new pH. Another caveat is you can't be past the equivalence point, right? So your strong acid or strong base needs to be the limiting reagent. If it's the other way around, then you've blown the whole buffer away, and now you have a whole different solution, which we'll get to later, how to calculate the pH of that. But here we're hoping that we still have some buffer left, so you can't add more strong acid or strong base than you have buffer. All right, so I'm going to finish with another example here. And so here we have hydrofluoric acid and sodium fluoride, and they're combined in this way. So you have a total volume of 500 mils, and then you have molarities to start of both HF and sodium fluoride. Now this means eventually we're going to have to convert these to moles, because when we do the stoichiometry, upon adding the strong acid, we need to do it in moles. So here 100 mils of some strong acid is added, and we want to find the new pH. Fun fact, if you get hydrofluoric acid on your skin, it'll soak through your skin, leach calcium from your bones, and then you die. Why I'm using it in a problem here, I have no idea. You would never do this in real life. But there's less letters when I'm doing a problem, so yeah, we'll use it. And so hydrofluoric acid is a weak acid, so it does what weak acids do. It takes water, makes H3O plus and fluoride. So we've got some stuff going on here. In the HCl, right, we write it as HCl, but it's really a bunch of H3O plus. This is a forward arrow, meaning that it completely dissociates and all of the HCl is turned into H plus or H3O plus, depending on how you want to call it. And then that neutralizes the fluoride, right? So these two react together. Again, forward arrow, because it's a strong acid. It does what it's going to do. No one's going to stop it. It's so strong. And this makes water and hydrofluoric acid. Okay, so you're turning the conjugate base into original weak acid. So that means you're going to have more of this and less of this. Another way to say it is that you take some of the fluoride and you turn it into HF. So, where are we at now? We need to do this stoichiometry first to turn the fluoride back into HF. So we got to find the moles of everything, right? The HF and the F were originally in this half-liter solution. And then the HCl, or H3O+, was originally delivered as 0.1 liters. So here we use these new quantities now in moles to then do our stoichiometry. So we're going to react away the fluorides. We're adding an acid, so we'll react with the conjugate base, and we're going to form HF, right? Just like we said before. So 0.1 moles of HCl is going to convert 0.1 moles of fluoride to HF. So it'll look like this. We make more acid, and then we make less base, right? Because you added a strong acid. When you're done, you're going to have less conjugate base than you had before. Okay, so now these numbers are what's present after you've done this addition of strong acid. And then that's what goes into Henderson-Hasselbalch to then do the pH calculation. So here's the numbers from the last slide. Here's the pKa, because we're going to need that. And then we plug the numbers in here. Remember, the nice thing about this equation is you can use just numbers of moles in it directly. Plug that in, right? The conjugate base F- is on the top. Weak acid, HF, is on the bottom. Great, here's your pH. So this is how you do this kind of problem. One closing thought is this, is that you could do this all with an icebox instead of doing the Henderson-Hasselbalch in the way that we just talked about it. It's just ridiculously tedious and you don't want to go there. All right, thanks for watching.